So we're learning how to use the periodic table, and the periodic table is actually useful for a lot of things. Even there's some stuff that we're not even going to get into yet, get into later, where the periodic table is very useful. Some new thing that we're going to talk about now that is very useful in the periodic table is the periodic table will actually help us predict ionic charges. So if we have some element that is either going to give up or take in extra electrons to become an ion, the location of that element on the periodic table will actually, in some cases, tell us what the charge is, and in other cases tell us what it most likely is going to be. We're going to focus on the ones where it is definitely telling us, because the ones where there's some uncertainty, if this were a higher level chemistry course, we would deal with those too, but since this is just Gen Chem, we're going to go with the ones where we know for sure what the charge is going to be based on this location on the periodic table. The trick to this is that every element, when it loses or gains electrons, is trying to become the same as a noble gas. It's trying to get the same number of electrons as a noble gas. Noble gases are very, very stable. This is why we call them noble, because they don't interact with the little elements. They're like, oh, look at the little elements down there. Oh, look at them. Oh, we don't interact with the little elements. And it's not because they're stuck up. It's because they're very stable. They don't need to interact with anything else. They're happy the way they are. So everything else is trying to get to be the same as that. They want to get the same number of electrons so that they can be stable, just like the noble gases. So, to do this, everything in column, so this is column 17 here, not 7a, or in the new numbering system it's 17. Everything in this column is going to gain 1 electron. I know that seems backwards because I wrote -1, but that's the charge that it's going to have. Because remember, electrons have a negative charge, and so because it is gaining an electron, it is going to end up with a negative charge as a result. Everything in this column is going to be -2. Because when it gains 2 electrons, so oxygen, for example, it has 8 electrons in its neutral state. It wants to be the same as neon, so it's going to gain 2, so it can have 10, just like neon. Everything in this column is going to be -3. Nitrogen will gain 3 to become the same as neon. Phosphorus will gain 3 to get 18, just like argon, and so on. This column's a bit weird. Sometimes it's +4, sometimes it's -4. So this one, and really most of the time it's +4. Because you only really have carbon up here that's non-metal. Carbon theoretically can be -4, but I'm not really aware of any time that happens off the top of my head, but I know it's theoretically possible. And then the rest of these down below here are metals, and if you remember from the previous video, metals are only going to be positive. So for the most part, this is going to be +4. This column is going to be +3. It's going to lose 3 electrons. Now you might be thinking, wait a second, we're talking about positive charges now, losing electrons? I thought they wanted to gain electrons to be the same as a noble gas. They want to have the same number of electrons as a noble gas, but that does not mean that they can only gain electrons to do it. If you notice aluminum here, aluminum has 13 electrons. Could it gain 5 electrons and become the same as argon? Theoretically, I guess, it's technically possible. Or, what's much easier than gaining 5 electrons, it's much easier to lose 3. If it loses 3, it will become the same as neon. And it's perfectly happy to do that. Actually, it much prefers to do that. So everything in this column is going to lose 3 electrons to become the same as a noble gas. We're going to skip over these because they're weird. There's not really a hard and fast rule for these guys to determine what their charge will be. But once we get over here, +2, and +1 are the charges that they are going to be. So in an ionic compound, if it's going to gain or lose electrons, everything in this column is going to lose 2 electrons to become the same as the noble gas. It's essentially flipping around the backside of the periodic table. Just because of the way that we have the periodic table drawn, it seems like, you get to the end of the line here and it's like, okay, no more elements. Like, actually, it's not technically correct. Like, there's element 36 here, but that then leads straight into element 37. The elements don't actually have to physically move to get from one side of the periodic table to the other. It's just because of the way it's drawn, it looks like there's a barrier here. Like you can't get from this side over to that side, but you actually can quite easily. So everything over here is going to lose 1 electron and become the same as a noble gas. And so that is going to be very, very useful to us, because there's going to be times later on in this chapter where we will need to figure out what the charge of a metal or the charge of a non-metal is going to be in a compound that is made up of ions. And simply by looking at the location of the element on the periodic table, we will be able to figure it out just like that. Exactly what the charge is going to be. Alright, moving on here. A few other interesting tidbits from the periodic table here. So most elements are what we call, well, actually we don't really have a special name for them. They're just plain old elements. The vast majority of elements, their basic unit is just a single atom. That is the simplest unit of that element. So carbon, for example, the simplest unit of carbon is just a single atom of carbon. But there are 7 very special elements that their basic unit is not just a single atom, it's actually 2. Their basic unit is 2 of the atoms bonded together. These are what we call diatomic elements. Just because we haven't really seen this before, I do want to point out here the difference between a subscript and a coefficient. So if I say that I have H, that is the same as me saying I have 1 hydrogen atom. If I put a 2 out in front of that, the 2 is saying I have 2 of whatever comes next. That's what a coefficient, that's what we call the number out in front. We call it a coefficient. So the coefficient is telling us I have 2 of whatever comes next. 2 separate things. So they're not connected together. It's like, if you, just because I have little kids and they like cars, if I say I have 2 cars, I'm not saying that I have 2 cars that are melded together, they're stuck together. No, it's 2 separate cars. That's what we're talking about here. There's 2 individual hydrogen atoms. Or if we had something bigger, so like this is methane, for example, CH4. If I put a 2 out in front of that, I'm not saying I have some giant molecule that has 2 carbons and 8 hydrogens in it. I'm saying, no, I have 2 different molecules of CH4. The subscripts, on the other hand, are telling you how many of that atom are in the molecule. So this is, in fact, saying inside of this thing there are however many of that particular element. So in this particular example, H2, that is saying I have a single molecule that contains 2 hydrogen atoms. If I put both of them in there, if I had 2 H2, that's saying I have 2 individual molecules of H2. So that's the difference between the coefficients and the subscript here. So in each of these 7, the basic unit of that element is this diatomic element. So for you to go out into nature and just find some bromine in nature, so it's not bonded to something else, it's not in a compound with something, it is just bromine. you will never find Br. Like, that's not the basic unit of bromine. It is always Br2. Same thing with N2 or O2. It is always that diatomic element. That is the what we call, the sciencey term is the free elemental form of that element. And so I do expect you to have these 7 memorized. Thankfully, it's really easy to remember which ones they are, especially if you have a periodic table handy. So if you can remember hydrogen over here all on its lonesome, and then the other 6 make a nice little 7 right here on the right side of the table. So if you can remember to not include the noble gases, so start at nitrogen, go to fluorine, go down to iodine, and then remember hydrogen over here. Those are your 7 diatomic elements. So it's not difficult to remember. Have a nice little 7 here, and hydrogen. Alright, originally I thought I was going to include this in this video, but I think I'll save it for the next one. So in the next video we will talk about atomic mass, how to calculate the atomic mass that is on the periodic table, and the strangeness of these atomic masses that are halves. How do you get half of a proton? I don't know. I guess we'll find out in the next video.